we've already teased the idea of needing to prove things in linear algebra here in our course, and we're actually going to go into that into a bit more detail right now. So what we have here is a mathematical theorem, and any mathematical theorem can be proved. It doesn't become a theorem unless there is a proof for it. And the way that we want to set up and prove mathematical theorems has a structure to it. And so I'm going to try to do a combination of talking through the structure of a mathematical proof while at the same time demonstrating how we can prove some of the vector operation properties. So for example, my first vector operation property right here says that addition's commutative. U plus v is the same as v plus u. Now this might seem like a given, but at the same time, it only becomes a given or a theorem because it is true for every single real number component of these vectors, and it's only true for every single vector in Rn. So that's what makes it a theorem. So for any proof, what we need to start with is we start by defining some of the variables or objects that we're going to be working with. So we're going to define vector u to be the components u1, u2, and because we're proving things in un, or Rn, and dimensions, we need to go to un. We also want a vector v, so we'll have v1, v2 to vn, and a vector w, w1, w2, wn. So with this, let's start by proving A. So we'll start by saying I want to show left-hand side equals right-hand side. So when proving show left-hand side equals right-hand side. Now, you're not going to do that for every single type of mathematical proof, but these ones where they say like equal to, so I've got this operation is equal to that operation, that's a perfectly good way to proceed. So we start by saying, well, u plus v. And I can actually write out what that is. So I've got u1 plus v1, u2 plus v2, and that goes all the way to un plus vn. And I was able to make that statement. This was that I used the definition of the operation to be able to say that that's what u plus v will look like. Well, because we know that real number addition is commutative, I could actually rewrite this as v1 u1, v2 plus u2, vn plus un. And then I can see from there that that would lead me to be able to say vector v plus vector u is equivalent. So all I've done is that I also here was use the properties. Wow. Use brain. Use the properties of basic algebra when dealing with real numbers. So let's do another example here. So I'm going to this time, well, what would it look like if I tried to prove B, which is u plus v plus w, and I want to show that I can actually write that as u plus v plus w in brackets. Well, in the question above, we actually already identified what u plus v is. It is u1 plus v1, u2 plus v2, all the way to un plus vn. And this time I'm adding w1, w2, all the way to wn. Well, using some, like we said, properties of real numbers and basic algebra, this becomes, I shouldn't have put a hat there, this becomes u1 plus v1 plus w1, u2 plus v2 plus w2, all the way to un plus vn plus wn. Okay, and so now that we have that, we can again, because we're just looking at the real number scalars inside the vector, I can rewrite that by changing the brackets, because this is a basic algebraic property of real numbers. And so I get u2 plus v2 plus w2 all the way to un plus vn plus wn. Okay, and from here we could actually take and bring u1, u2, all the way up to I'm sorry, un out in front, and add that to v1 plus w1, v2 plus w2, vn plus wn, and we are left with u plus v plus w. In that situation, now both of these proofs that I've shown above involve just the vectors. I'm going to jump down and I'm going to show e, because e actually includes a scalar. So it's k u plus v. And I want to show that's the same as if I distributed the scalar inside to both u and v. Well, that's the same as saying k times u1 plus v1, u2 plus v2, un plus vn. And so if I distribute that inside, so u1 plus v1, k u2 plus v2, k un plus vn, and then I've got ku1 plus kv1 and ku2 plus kv2 and kun plus kvn. All right, well, I could now rewrite that as ku1, ku2, kun plus kv1, kv2, kvn, leaving me with ku plus kv. So here's 3 examples. I'm going to say the rest are left as an exercise for you to practice on your own with your proofs, because this is something that you will need to know how to do for this course. Now on our next page, we again have another theorem that we're going to look at. This is a theorem based on our zero vector and our additive inverse, or our negative vector. So in this case, I'm only dealing with one vector, so when I define what I need, I'm just going to define v and let v be v1, v2 to vn. So I've defined what my vector v looks like. So for a, if I'm saying, okay, 0 times v, Well, that would be the same as if I took 0 and I multiplied it to each of the components inside my vector v. And from there, I could see, well, anything multiplied by 0 is just going to be 0. And I will be then left with the 0 vector. Very similar for b. I'm going to go k times the 0 vector. Well, that'd be the same as going k times 0, k times 0, k times 0. And just to point out, we would have n components here. And this leaves us with 0, 0, 0, n times again. And that is also our 0 vector. Now I'm going to leave C as an exercise for you to practice on your own. And if you have any trouble, you of course come and ask during office hours.